Special theory of relativity. At 26 years old, Einstein proposed that the laws of physics are the same for all non-accelerating observers and that the speed of light in a vacuum is constant, regardless of the observer's motion. For instance, imagine you're on a train moving at a constant speed and you shine a flashlight forward. According to Einstein's theory, if someone standing still outside the train were to measure the speed of the light beam from the flashlight, they would find it to be the same as if the train were stationary. This theory revolutionized our understanding of space, energy, and time. Photoelectric effect. In 1905, Einstein extended Planck's hypothesis to explain the photoelectric effect. This effect explains how light can eject electrons from a material's surface. Contrary to classical physics, which predicted light energy to be continuous, Einstein proposed that light comes in discrete packets called photons. This proposal is also known as the quantum theory of light. When light shines on a material, photons transfer their energy to electrons, allowing them to escape. This discovery laid the groundwork for quantum mechanics and earned Einstein the Nobel Prize in Physics in 1921. Wave-particle duality. Light behaves both as a wave and as particles called photons. It introduced the idea that particles, such as electrons, manifest wave-like properties and that the behavior of matter at the atomic scale is fundamentally different from classical physics. Mass-energy equivalence. This equation is considered by many the most important physics equation in history. E equals mc squared demonstrates the equivalence of mass and energy, implying that mass can be converted into energy and vice versa, proving that they are basically different forms of the same thing. E equals mc squared is so powerful because it laid the groundwork for the development of nuclear energy. Inertia of energy. Inertia is the property of matter that resists changes in motion. This principle, as described by Newton's laws of motion, explains how objects maintain their state of rest or uniform motion unless acted upon by external forces. When considering mass-energy equivalence, we understand that mass and energy are interchangeable. Therefore, just as mass exhibits inertia, energy also resists changes in its state. This concept implies that energy, which is inherently linked to mass, contributes to the gravitational attraction of objects, as described by the theory of general relativity. General theory of relativity. When Einstein proposed his special theory of relativity, he did not consider gravity. Adding what is known as Einstein's field equations, he created the general theory of relativity, redefining gravity as the curvature of space-time caused by mass and energy. It explains how objects with mass warp the fabric of space-time, influencing the motion of other objects. This theory offers new insights into phenomena like the bending of light around celestial bodies and the dynamics of the universe on a large scale. Gravitational waves. As a consequence of his general theory of relativity, Einstein predicted the existence of gravitational waves in spacetime caused by the acceleration of massive objects. These waves were directly detected for the first time in 2015. The most incredible aspect of this discovery is that the idea of gravitational waves was theorized in 1916, 99 years before it could be physically detected. Cosmological constant. Einstein, in order to make the equation of general relativity work, had to add a constant. The function of this constant was to stabilize the universe and make it a static universe. This constant, known today as the cosmological constant, was called by himself his biggest blunder. Why? Edwin Hubble, years after Einstein's theorizing, proved that the universe is expanding. So, Einstein removed this constant, calling it precisely his biggest blunder. Decades later, it was discovered that there is a force in the universe that acts against the force of gravity and causes the expansion of the universe to accelerate. To take this force into account, there was the need to add back into the equation what Einstein believed was his biggest blunder. Equivalence principle. The equivalence principle serves as a foundational concept for understanding gravity in general relativity. It states that the effects of gravity are locally indistinguishable from the effects of acceleration. Imagine this situation. There are two identical rockets. The characteristic of these two rockets is that they do not have any windows, and no noise or vibration can be heard inside, so you cannot hear whether the rocket is ignited or not. One rocket is on the Earth, completely stationary. The other rocket is in space, with a constant acceleration equivalent to the gravitational acceleration present on Earth. The equivalence principle explains how in this scenario it is impossible to tell the difference between the force of gravity and the acceleration of the rocket. So if I teleported you into either rocket suddenly, you would not be able to tell in any way whether you were in the stationary rocket on Earth or the rocket in space. If you tried to drop an apple on the ground, the apple would fall at the same speed in both rockets. EPR paradox. In collaboration with Boris Podolsky and Nathan Rosen, Einstein formulated the Einstein-Podolsky-Rosen paradox in 1935. The paradox revolves around the concept of quantum entanglement, where two or more particles become correlated in such a way that the state of one particle instantly influences the state of another, regardless of the distance between them. This idea appeared to contradict Einstein's theory of relativity, which says nothing can move faster than light. This paradox made a lot of people question if quantum mechanics was missing something important. Unified field theory. Einstein spent much of his later career searching for a unified theory that would include all fundamental forces of nature, along with gravity and electromagnetism. While he never fully realized this goal, his attempt paved the way for later advancements in theoretical physics, such as string theory and quantum gravity. Bose-Einstein statistics. In collaboration with the Indian physicist Satyendra Nath Bose, Einstein developed Bose-Einstein statistics. These rules explain how identical particles, such as photons or subatomic particles, act in quantum physics. Unlike regular particles, they can be in the same place at the same time. These statistics were important for understanding how particles behave in cold temperatures and dense environments, which has helped us in fields like quantum optics and the study of condensed matter. Theory of critical opalescence. Critical opalescence theory explains why substances appear cloudy near certain temperature and pressure conditions, known as critical points. These critical points mark when substances change from one phase to another, like from liquid to gas. Opalescence refers to the increased scattering of light in these conditions. Quantum theory of solids. Einstein helped us understand how atoms behave in solids, especially how heat affects them. In 1907, he suggested a model where atoms in a solid act like tiny swinging pendulums. This model explained how solids heat up differently at low temperatures compared to what was expected before. Einstein also showed that vibrations in the solid structure act like tiny bundles of energy, kind of like how light behaves as photons. This idea helped us grasp how heat moves through solids. Brownian motion. Einstein used the Brownian motion, proving mathematically for the first time ever the existence of atoms. But not only that, he also managed to figure out how to calculate the size of atoms based on how much the Brownian particles moved. Einstein refrigerator. In 1926, Einstein and his former student Leo Szilard patented the Einstein refrigerator, which operates on the principle of absorption refrigeration. It was designed to be safer and more efficient than conventional refrigerators of the time, using a closed-cycle absorption system that required no moving parts and thus had minimal risk of leaks or mechanical failure.